Okay, hi everyone. In this video, we're going to go ahead and talk about phase changes and how they relate back to that topic of intermolecular forces. So first off, I want to do a quick review about phase changes. Okay, so here I have a solid, a liquid, and a gas. So the gray ones, that's the solid where they're tightly packed, they're just vibrating in place. The blue spheres, those are the liquids. The liquid particles, they move around a little bit. Unlike the solid, they're not locked in location. And then on the right-hand side, those red spheres, we have the gas particles that are moving very, very quickly. And there's a lot of space in between them. This picture is actually a little misleading. There'd be a lot more space between them. So if we think about the different phase changes, okay, going from solid to liquid, that is melting. Liquid to gas, that's evaporation, which is also related to boiling. So either one's okay. Going from the gas to the liquid, that is condensation. And then from the liquid to the solid, that is freezing. So those are the ones that we think about most often, but there are two other ones that also exist. And those are going from the bottom, from the solid to the gas. That is going to be, anyone? Sublimation. Okay, and then going from the gas to the solid, I always think I'm depositing something, so that one is deposition. Okay, so sublimation and deposition are the other two phase changes we can have. In these, we don't go through the liquid phase in the middle, we just go from one directly to the other. Okay, so the other thing I want to point out and remind you, remember temperature and kinetic energy are related. And temperature is actually the measure of the average kinetic energy of the particles in a substance. Keyword here is average, okay? So substances that have a higher temperature have more kinetic energy on average, and the particles will move around faster and move around more than those at a lower temperature. Again, remember I said that was an average kinetic energy. In a sample, the individual particles of that substance will travel at many different speeds. And we're always going to have some that move very slow and some that move very fast. It just so happens that in hotter substances where the temperature is greater, we tend to have more of those fast particles and less of those slow ones. However, even in cold substances, there are still a few particles that have high kinetic energy. It's just overall, the majority of the sample doesn't. So if you look at this picture, it probably seems a little odd. Why would people be drying their clothes on a clothesline in the middle of winter, right? We know in the summertime it dries off really fast, but in the winter, this doesn't even seem possible. Well, it is because we have some of those particles that are still moving really, really fast, even though the temperatures are slow. So it might take longer for the clothes to dry out being outside in the wintertime, but they actually can dry even if it's below freezing. Okay, so let's actually go ahead and think about phase changes and relate those back to intermolecular forces. Okay, so I have a question for you to think about. Does the kinetic energy change with the phase? We go from a solid to a liquid or a gas. So go ahead, pause for a few seconds, come up with an answer in your mind. Okay, so the answer is yes. As we go from a solid to a gas, the kinetic energy usually increases. There are a few exceptions, but those are kind of more the oddball examples. So generally, as we go from a solid to liquid gas, kinetic energy increases. And as we go from a gas to a liquid to a solid, usually we cool things down so that kinetic energy decreases. Next question. Do intermolecular forces change with the state, solid, liquid, or gas of a substance? So go ahead, think about it, come up with an answer, pause the video if you need to. And the answer for this is no. Intermolecular forces are based upon the structure of the molecule. Okay, so that stays the same. We're not changing the shape of the molecule just because we're going from a solid to a liquid to a gas. However, the relative relationship between the kinetic energy and the intermolecular forces does change. So the kinetic energy changes, but the intermolecular forces stay the same. But because one's changing, we do get a changing relationship between the two. So in solids, the intermolecular forces are much greater than the kinetic energy. That's why the particles are pretty much held in that one location. They vibrate, but they can't break free. They can't really move around because the intermolecular forces hold them in place. In a liquid, the kinetic energy is a little bit greater than the intermolecular forces. Not a lot, but just a little bit. So that's why the particles are still close to one another because we still feel those strong intermolecular forces comparatively, but the kinetic energy is high enough that the particles can now move a little bit. And then in gases, the kinetic energy is so much greater compared to the relative intermolecular forces. That's why there's a lot of space and the particles are moving really, really quickly. Okay, so one thing I want to point out is the difference between ionic and covalent compounds when it comes to phase changes. Okay, so remember, ionic compounds are held together by ionic bonding. There are no intermolecular forces because they don't have molecules. Remember, they're crystalline solids, not three-crystal lattice. So during phase changes for ionic compounds, we need to either make or break ionic bonds. And since ionic bonds are so strong, that's why ionic compounds often have high melting and boiling points. In comparison, covalent compounds, they form discrete molecules, individual molecules. And within those molecules, they have intramolecular forces, but between molecules, we also have the intermolecular forces. So they have two things going on. Now, if we compare the intramolecular forces, the bonding, to the intermolecular forces are so much weaker. So when covalent compounds go through a phase change, we are actually playing around with that intermolecular force. We are kind of overcoming it or reforming it as those molecules come together. So with covalent compounds, the covalent bond is not made or broken during phase changes. That stays the same. What we play with, what we change, is the intermolecular force for covalent compounds. Ionic compounds, that's when we're making or breaking bonds. Okay, so the physical state of a substance is determined by the amount of attractive and repulsive forces that the substance is experiencing. So attractive forces, usually those are the intermolecular forces, and that's what causes the particles to clump up or want to stick together. Versus repulsive forces like the kinetic energy or the movement of those particles causes the particles to want to push further away from one another. And when the kinetic energy increases, the particles will push further apart, meaning the substance will either melt or evaporate. But when the kinetic energy decreases because the temperature is dropping, the intermolecular forces, they are now the dominant force. So the substance is going to start to condense and then freeze. Okay, so just kind of the interrelationship between those two ideas, what's pushing apart and what's pulling it together, and which one's greater. Okay, so let's think about the properties of solids, liquids, and gases and how those relate to intermolecular forces. Okay, so for solids, remember the intermolecular forces are much greater than the kinetic energy. So we know that solids have a high density. This is because the intermolecular forces hold the particles close together. Particles close together means high density. Solids are not compressible, so because the particles are already held together closely, there's not a whole lot of space they can really get closer unless they start to overlap their electron clouds, which atoms don't really like to do because remember, electrons are negatively charged and opposites attract, like charges repel. So electron clouds will repel each other. For liquids, the kinetic energy is slightly bigger than the intermolecular force. Now, if we think about liquids, they are denser than gases, but less dense than liquids. Less dense than solids. This is because the intermolecular forces hold the particles together, but not as tightly as in a solid. They're relatively incompressible because even though they're able to move, there's still not a whole lot of space between those particles. And again, the electron clouds will repel the different atoms. Liquids can diffuse, meaning they can mix together, but this is going to happen at a slower rate than gases. That's because they have a lower kinetic energy. Okay, so the higher the kinetic energy is, the faster the particles move around. Now for gases, the kinetic energy is much greater than the intermolecular force. This is why gases are the least dense phase. The particles are spreading out because they have so much kinetic energy they want to move and get their extra space. But they're very compressible. We don't have to worry about the electron clouds overlapping as much because we have so much space between those particles. And they will diffuse quickly to fill the container. That's because they have that high kinetic energy. They want to spread out. They want to move and fill up the space. Okay, so if we think about this idea, intermolecular forces versus kinetic energy, we can use this to kind of explain some data that we see. So as we look at these molecules, we have ethane, butane, hexane, octane, and decane. We see that they all have a chemical formula containing carbon and hydrogen, okay? So if we think about the polarity, carbon-hydrogen bonds, those are nonpolar. So all of these molecules are nonpolar, okay? So I want you to think about their masses, intermolecular forces, and how that relates to the boiling point and melting point. So kind of on your own, pause the video, try and explain this data, and then we'll go over in a few seconds. So pause the video, think, come up with an answer by yourself, and then we'll check in a second. Okay, so when we think about these molecules, they only have London dispersion forces because they're nonpolar bonds. So we can't have hydrogen bonding. We don't have dipole-dipole interactions. We only have LDFs. So we think back, the amount of LDFs or London dispersion forces increases as the mass of our substance increases. So that means that the decane C10H12 will have greater London dispersion forces than the ethane C2H6 because the molar mass of the decane is greater than the molar mass of the ethane. And as we look at the boiling points and the melting points, we see that trend fitting in. It takes more energy to overcome the greater London dispersion forces in decane than it does to overcome the London dispersion forces in ethane. So decane has a higher boiling point and a higher melting point. Okay, let's try another one. Okay, so for this, I want you to, again, pause the video, but think about what intermolecular forces you have, think about their strengths, and use that to explain the data. Okay, so when we look at these examples, water is different from all the other molecules here because water has hydrogen bonding. Remember, for hydrogen bonding, we need a hydrogen bonded to either a fluorine, an oxygen, or a nitrogen. In this case, it's the OH there. So water is able to hydrogen bond. In fact, it will form 4 hydrogen bonds with its neighbors, which is a whole lot of them. So water is really good at hydrogen bonding, and it has LDFs. The other molecules are all nonpolar, so they only have London dispersion forces. So remember, hydrogen bonding is so much stronger, that means it's taking more energy to overcome that intermolecular force. This is why water has such a high melting and boiling point compared to other molecules. Okay, so if we look at this, water has basically half the molar mass of H2S, but it is significantly higher for its melting and boiling point, which is a good thing for us. This is why we're able to have liquid water on Earth, which I don't know about you, but I really love being able to have water in liquid form instead of just having it as a gas. And that's what really makes life possible as we know it. So since water is the only one that hydrogen bonds, water has an abnormally high melting and boiling point for its mass. So I hope this helps. If you have any questions about how we can relate phase changes to intermolecular forces, please let me know. But remember, the takeaway for today, stronger intermolecular forces, more energy needed for melting and boiling point changes, so therefore the greater melting and boiling point. If you have any questions, please let me know. Bye, everyone.